Hi everyone. Really quick lesson this week. It's dealing with Pascal's triangle and how it works with pathways. Light lesson, not a lot of homework this week. As you've all seen by now, there's no school for regular classes on Friday, so there's going to be no quiz this week. Kind of get the homework done, and we will have our Zooms on Wednesday, but other than that, it should be fairly light. So recall Pascal's triangle, 1, 1, 1, 2, 1, 1, 3, 3, 1, etc. We looked at a problem the other day where we used permutations to help us figure out how many ways there were to get from point A to point B. 3 north blocks, 5 west blocks. This we said was 8 factorial over top of. The 3 and the 5 really don't matter because they're all exactly identical, so we use that formula. Well, now what we're going to do is we're going to look at it as how many ways to get to a certain spot using, well, to begin with, we just count the ways, and you can see there's 2 ways to that second spot, 3 for the next ones, and as you continue to build it, you notice that Pascal's triangle is sitting there kind of on an angle, but you should be able to see how it does produce this exact same solution for us that worked out with that permutation model. Permutation model's faster, definitely, but what if we look at a pathway problem where there aren't a nice number of ways to get from one block to the next? Maybe there's some trees in the village, a couple of different sets of them perhaps. The permutation model won't work because we don't have continuation where we can say any block can be done at any time. Maybe our village is complicated enough that it's got a river running through it with a few bridges, as I'm showing you here on the diagram. I'm actually having fun with this lesson, as you can tell. Throw a bridge here. And one more, I think. That should be good. And let's take out that middle section and let's turn it into a little park. Place for the kids to play. So, how many ways to get from A to B? Well, the first part flows exactly the same as the rest, just Pascal's triangle as usual. But the next, you'll notice that when I cross the bridge, all of the 6's I just wrote down, I can only get there by crossing the bridge and then continuing on. So there's no way to create this without having to do that little bit of extra. I did break the rules a little bit because I went down when technically I should have just gone straight across. But I'm just trying to give you an overall impression of how this would look. As you can see, the numbers are building fairly quickly, but you have to do each side of the river on its own. I would encourage you occasionally, freeze this video, take a look at the numbers, make sure you're understanding how each of them are created by adding from below and from the left. Because ultimately to get from A to B, if we're looking at where we are in B, we have come from below and from the left. So we keep adding them together. Almost done here. So a few extra city blocks compared to our other problems, but also these potential problems with the river, the trees, all that sort of thing. And we can see that we end up with just about 4,000 ways to do it. Homework. I'm just asking you to do a couple of problems out of the textbook. Number 8 we've already done, but I want you to do it the Pascal triangle way. Page 548 is something new. And let's take a look at Kamloops. How many ways are there to get from my starting point that I've marked off on the map to Denny's, my finishing point? That's all I've got for today. I was writing out exactly what I said. That's all I've got for today, so give it a try, see how it goes. Just remember, it's just like creating Pascal's triangle. Add the 2 numbers to get to the next spot. If only one of those spots is available to you, you're only carrying over 1 number, and that's how those 6's ended up being there. All right, that's it. I'll see you on Wednesday. Enjoy the week. Goodbye.